Something strange is happening to our planet. The Earth is heating up faster than ever before. But this isn't just a modern story. The roots of this strange warming stretch back through history, science, and human choices. Today, we'll uncover how Earth's climate has shifted, why it's heating unnaturally fast, and what history tells us about the future. In the 1800s, scientists like Joseph Fourier first described the greenhouse effect, the idea that gases in the atmosphere trap heat. The greenhouse effect occurs when heat-trapping gases in a planet's atmosphere prevent the planet from losing heat to space, raising its surface temperature. Surface heating can happen from an internal heat source, as in the case of Jupiter, or come from an external source, such as a host star. In the case of Earth, the sun emits shortwave radiation, sunlight, that passes through greenhouse gases to heat the Earth's surface. In response, the Earth's surface emits long-wave radiation that is mostly absorbed by greenhouse gases, reducing the rate at which the Earth can cool off. Without the greenhouse effect, the Earth's average surface temperature would be as cold as -18 degrees Celsius -0.4 degrees Fahrenheit. This is of course much less than the 20th century average of about 14 degrees Celsius 57 degrees Fahrenheit. In addition to naturally present greenhouse gases, burning of fossil fuels has increased amounts of carbon dioxide and methane in the atmosphere. As a result, global warming of about 1.2 degrees Celsius 2.2 degrees Fahrenheit has occurred since the Industrial Revolution, with the global average surface temperature increasing at a rate of 0.18 degrees Celsius 0.32 degrees Fahrenheit per decade since 1981. Later, Svante Arrhenius calculated that burning coal could warm the Earth. At the time, many thought a warmer planet might be beneficial. Earth has always warmed and cooled. Ice ages, warm interglacial periods. But here's the strange part. Past warmings took thousands of years. Today, Earth has warmed about 0.7 degrees Celsius in just a century, nearly 8 times faster than natural cycles. All objects with a temperature above absolute zero emit thermal radiation. The wavelengths of thermal radiation emitted by the Sun and Earth differ because their surface temperatures are different. The Sun has a surface temperature of 5,500 degrees Celsius 9,900 degrees Fahrenheit, so it emits most of its energy as shortwave radiation in near-infrared and visible wavelengths, as sunlight. In contrast, Earth's surface has a much lower temperature, so it emits long-wave radiation at mid- and far-infrared wavelengths. A gas is a greenhouse gas if it absorbs long-wave radiation. Earth's atmosphere absorbs only 23% of incoming shortwave radiation, but absorbs 90% of the long-wave radiation emitted by the surface, thus accumulating energy and warming the Earth's surface. The existence of the greenhouse effect, while not named as such, was proposed as early as 1824 by Joseph Fourier. The argument and the evidence were further strengthened by Claude Pouillet in 1827 and 1838. In 1856, Eunice Newton Foote demonstrated that the warming effect of the sun is greater for air with water vapor than for dry air, and the effect is even greater with carbon dioxide. The term greenhouse was first applied to this phenomenon by Niels Gustav Ekholm in 1901. The greenhouse effect on Earth is defined as the infrared radiative effect of all infrared-absorbing constituents in the atmosphere, greenhouse gases, GHGs. Clouds and some aerosols absorb terrestrial radiation emitted by the Earth's surface and elsewhere in the atmosphere. The enhanced greenhouse effect describes the fact that by increasing the concentration of GHGs in the atmosphere, due to human action, the natural greenhouse effect is increased. His graph, the Keeling Curve, showed CO2 rising year after year. This was the smoking gun. Human activity was heating the Earth. Animation of the Keeling Curve rising. Footage of cars, planes, factories. The term greenhouse effect comes from an analogy to greenhouses. Both greenhouses and the greenhouse effect work by retaining heat from sunlight, but the way they retain heat differs. Greenhouses retain heat mainly by blocking convection. In contrast, the greenhouse effect retains heat by restricting radiative transfer through the air and reducing the rate at which thermal radiation is emitted into space. John Tyndall was the first to measure the infrared absorption and emission of various gases and vapors. From 1859 onwards, he showed that the effect was due to a very small proportion of the atmosphere, with the main gases having no effect, and was largely due to water vapor, though small percentages of hydrocarbons and carbon dioxide had a significant effect. The effect was more fully quantified by Svante Arrhenius in 1896, who made the first quantitative prediction of global warming due to a hypothetical doubling of atmospheric carbon dioxide. The term greenhouse was first applied to this phenomenon by Niels Gustav Ekholm in 1901. In 1896, Svante Arrhenius used Langley's observations of increased infrared absorption where moon rays pass through the atmosphere at a low angle, encountering more carbon dioxide, CO2, to estimate an atmospheric cooling effect from a future decrease of CO2. He realized that the cooler atmosphere would hold less water vapor, another greenhouse gas, and calculated the additional cooling effect. He also realized the cooling would increase snow and ice cover at high latitudes, making the planet reflect more sunlight and thus further cool down, as James Krall had hypothesized. Overall, Arrhenius calculated that cutting CO2 in half would suffice to produce an ice age. He further calculated that a doubling of atmospheric CO2 would give a total warming of 5 to 6 degrees Celsius. Thermal radiation is characterized by how much energy it carries, typically in watts per square meter. Scientists also measure the greenhouse effect based on how much more long-wave thermal radiation leaves the Earth's surface than reaches space. Currently, long-wave radiation leaves the surface at an average rate of 398 W/m2, but only 239 W/m2 reaches space. Thus, the Earth's greenhouse effect can also be measured as an energy flow change of 159 W/m2. The greenhouse effect can be expressed as a fraction, 0.40, or percentage, 40%, of the long-wave thermal radiation that leaves Earth's surface but does not reach space. Strengthening of the greenhouse effect through additional greenhouse gases from human activities is known as the enhanced greenhouse effect. As well as being inferred from measurements by ARGO, Ceres, and other instruments throughout the 21st century, this increase in radiative forcing from human activity has been observed directly, and is attributable mainly to increased atmospheric carbon dioxide levels. CO2 is produced by fossil fuel burning and other activities such as cement production and tropical deforestation. Measurements of CO2 from the Mauna Loa Observatory show that concentrations have increased from about 313 parts per million ppm in 1960, passing the 400 ppm milestone in 2013. The current observed amount of CO2 exceeds the geological record maxima, almost equals 300 ppm, from ice core data. Over the past 800,000 years, ice core data shows that carbon dioxide has varied from values as low as 180 ppm to the pre-industrial level of 270 ppm. Paleoclimatologists consider variations in carbon dioxide concentration to be a fundamental factor influencing climate variations over this timescale. Hotter matter emits shorter wavelengths of radiation. As a result, the Sun emits short-wave radiation as sunlight while the Earth and its atmosphere emit long-wave radiation. Sunlight includes ultraviolet, visible light, and near-infrared radiation. The relative sizes of the greenhouse effects on different bodies cannot be predicted simply by comparing the amount. On other planets, pressure broadening means that each molecule of a greenhouse gas is more effective at trapping thermal radiation if the total atmospheric pressure is high, as on Venus, and less effective at trapping thermal radiation if the atmospheric pressure is low, as on Mars. Something strange is heating up the Earth, but it's not a mystery anymore. History, science, and evidence point to us. The question is, will we change the story before it's too late? If you found this video eye-opening, hit like, subscribe, and share. Let's spread awareness.